before we introduce the speaker.
So, ladies and gentlemen, a very warm welcome, and thank you very much for having us here and having the possibility to introduce to the company, but mainly to the technology. I'd like to introduce our team, and we have our main speaker later on, Henrik Holf. He's Global Product Manager for Enviro, and Max Hübach, he is Product Manager in our subsidiary in Shanghai. And with that, yes, I want to wish you a good presentation, and whenever you have questions, just feel free to.
Yeah. Thank you very much for your introduction.
You would like to introduce you first?
You would like to introduce me?
No, it's okay. If you want to carry on, introduce yourself.
Henrik Holf. I'm product management at Pallas in Karlsruhe at our headquarters. I'm responsible for environmental products, means everything that has to do with air quality measurement. And today I would like to show you more about our technology in first instance, but also some applications. As Volker already said, in case there are questions to the technology or to any other topic, you can instantly ask. I mean, we have time enough, I suppose. And so just ask. Yeah, thanks. Some words about Pallas will come up front so that you see where we are coming from and what our vision is. And trends and innovation, what drives us currently in Europe, especially Pallas and spectrometry. So everything what has to do with optical particle counting and sizing. This is the most important topic, actually also for us, because most of the devices are based on that technology. Nanotechnology as well. So ionization particle counters, just a glimpse, and also SMPS systems, and some alternatives to ultrafine particle measurement diffusion charging. So this will also be very short. Because this is very important to understand also. And what we do different to us. Our vision, every company has a vision. So ours is actually a clean, healthy, and sustainable environment. I think this is something which everybody drives right now, also in India. On several conferences I saw and I heard that this is a very, very important topic, also for you, of course. There's lots to do. In Europe, we are one step ahead, so we don't have these high dust concentrations anymore. We had them in the past as well. And measurement and correct measurement of dust and also other substances is one of the most important for mitigation strategies. We are placed, or our headquarters is in Karlsruhe. So this is in Germany up here, quite far away. And we have a subsidiary in Shanghai in China for the local market, which is a very important market for us as well. And sales partners all over the world where air quality and our devices are used. But air quality, but also other devices. What drives us in terms of air quality and pollution? Clearly, that recently we saw that besides, at least for Europe, PM2.5 and PM10, there are metrics which are still very important. But we also see that ultrafine particle measurement and black hole measurement is coming more and more. Out of the directives, which was recently published in October 2024, there's a new focus. Real-time high-resolution monitoring, high resolution and at lower limits is also a very important topic. You know, every device has uncertainties, and the lower the values go, the measurements go, the higher the uncertainties are. The question is also for us, or was for us, can we cope with lower limits and lower concentrations? Can we meet the uncertainties which are given in the specifications or in the standards for the European Union? Multi-pollutant stations is also a topic for hotspot measurement, for example. So what we do here, integrating other devices into existing devices or attached to them. It's a topic which we see, which is coming more and more. And a very important topic, remote operation and control, on-site calibration and adjustment. Means devices, especially the optical devices, they have very specific features which help to ensure that the measurements are correct. And in addition to that, make it easy on-site to calibrate and adjust them on-site. So calibration, I will show this. We can also then, if you like, can do this by yourself at our small device, feeders rock. The bottle has a certain substance in it, and I will explain what kind of substance we use for calibration. And in addition to that, flexible miniaturized low power systems, ease of use with low uncertainty. This is a topic, we have an existing measurement network in Europe and also in other countries, and enhancement of those with new parameters is sometimes tricky because there's no space, there are no route plans available, whatever. So we miniaturized one of our systems in the direction that it can be used as a regulatory monitoring system also directly in. I already mentioned European Union or the European Commission or published a new directive, and states at the World Health Organization's limits to a certain extent, but not fully, of course, because they are very strict. But what the World Health Organization in the past always said and recommended where urgent actions are needed is the revision of the limits. This was done in Europe, especially after a long time. Very important, increasing number of monitors in general. Also something Europe is now following, increasing number of PM2.5 locations. Not all stations measure PM2.5, and there were also no daily limits in the past, only yearly average limits. So this changed. So more PM2.5 stations, European monitoring, of course, in super sites, but also as hotspot measurement at certain areas, indicative measurements. And one big topic is black carbon monitoring. I will focus on the lower limits, on more PM2.5 stations, following our concepts and requests of the measurement of UP in super stations and hotspots. Good. Pallas and spectrometry, that's actually where Pallas came from. Pallas is a company which was found, which was a spin-off from the university in Karlsruhe, from the KIT, Karlsruhe Institute of Technology, formerly Technical University. And these people who were at a certain institute, they developed that principle, which we are still using since many years for our particle measurement. And there are some implications. I will just jump in here. So these are the devices which where we use such kind of spectrometry with polychromatic light. I will come to that back later. So that's our regulatory monitoring device. We sold more than, better, 6,000 in the past. Not only within Europe, but also in other countries. And we have our indicative monitoring system, MCERT certified. That's a standard which is coming from the UK for indicative measurements, and to that we can also attach particles and measurement of gases, for example, NO2 or 3. And then we have smaller devices like Equivalent Frog, Feeder's Frog, which is standing here, and another device for indoor measurement. In addition to that, we use spectrometry, of course, also in our industrial systems. Here you can see in front of you the promo system. That's one of the outcomes of the development. Sensors which are separated from the main unit. Here in this case, 2 sensors, and they are predominantly used for filter measurement, for filter efficient measurement in filter media and filter elements. For especially if it's about optical particles which can be measured optically. And in addition to that as well, some specialties like cloud droplet analyzer. So that's a device which is used in higher altitude, where clouds typically are existing, to analyze the size of the particles of clouds in different altitudes. So we've made different campaigns with that device. I will come to that also later. And also some very special devices like Raspberry meter. This was an instrument here, which we used to measure concentrations and size distribution of exhaled particles from the lung during COVID. This was a study, so we never study actually, and we did not industrialize it finally, but proved that if people are ill and have lung diseases, some of them are super spreaders, and they exhale quite a lot of particles, and you could see this easily with that device. So you can be infected, but not exhale higher concentrations of particles, but then you are not infectious to others, or it can just be also the opposite. And we used during COVID this device by ourselves as experiment for those who want to test themselves before they enter our site. Same for mask testing. Here, similar technology, spectrometry to test filter efficiency of masks. This was not against the standard, which is typically used for that, but as we can measure fractional efficiency of masks, this is a very important factor, especially if it's about viruses, because they're very small. And then you want to know the effect of the filtration efficiency, especially in the lower area, and not the total efficiency, which is typically measured. Where are we located with our devices, or where are our devices used? And you can see here, more or less everywhere. They are used. Can be in the Antarctica, also the cloud droplet analyzer. Can be volcano observations in La Palma, for example, with the outbreak of the volcano. On La Palma, we measured together with the authorities. They asked us to fly over, bring devices for to observe and also to inform in case there are eruptions and where are high concentrations to be expected. And also other topics, we measure on glaciers dust, which is transported by wind, by convection, and also in other areas. Let it be, this can be also in deserts. This is a desert station from a European project called Fragment. And also we observe such kind of phenomena like Sahara dust transport. Sahara dust, which is transported to Europe. We can clearly see this with our devices as we do high-resolution particle tests. Our systems are used for brake emission testing, new standard in Europe. Here, especially ultrafine particles. And of course, also such kind of public seaport emissions directly into seaport or airport. So we're measuring, for example, the decay time of concentrations in rooms. We have a model where calculate on the efficiency of the HVAC systems and the cleaning, which was also important during COVID. The tie-up ratio is a pretty new project together with a university in Switzerland, in Bern. It's cabin air quality measured via stroke, and as said, environmental measurement or environmental monitoring, especially throughout Europe, but also in other countries, is one of the most important topics and applications which we serve. And last but not least, filter test systems, different kind of filter test systems, measuring ultrafine particles, filter efficiency of HEPA filters, or standard efficiency of standard medium, which are HEPA. And then it is optical measurement systems. Yeah, core capabilities, and we will dig into that a bit deeper then also. Our spectrometers, the size range which we serve is from 120 micrometers or nanometers up to 100 micrometers, depending on the device and the sensor we use. We can cover particle number concentration ranges from 0, next to 0, or actually 0, 10 power 7 particles, also depending on the type of sensor and instrument. We use for spectrometry typically polychromatic light, so we don't use laser sources. There's a reason behind, I will tell you later. And we have high resolution sizing with 256 channels over typically 2 decades. No border zone error. This is something which is also very important for our devices. What does it mean? If you have an area where light scattering takes place, at the edge of the area, the light intensity might differ, and we can identify it whether particles are in that area or not, and then not take them for sizing or for the size distribution. Only those which are measured in the middle, where the light intensity is the highest. Full on-site calibration against NIST traceable particles. Also very important topic for environmental measurement, but also for all our devices which are used for spectrometry. Drift detection is also something which is very important for environmental measurement. So if you see channel drifts of the system, means due to optics or LEDs which degenerate, or optics which are spoiled, you have less reflection and the particle size seems to be smaller. And this we can see with our system if there is something happening in that area. And of course, we need to meet new regulations on particulate matter limits. In terms of uncertainty, this is what the topic we can talk about at the beginning. And here I will show what is behind the topic. Spectrometry with polychromatic light. All the sensors have more or less the same structure as the one you can see here. Yeah. We have one light source, here in this case an LED light source. This is a more blue LED. Here in this device, it's a xenon source, xenon light source, which is much more bright. Our sensor is equipped with a so-called T-shaped aperture on both sides. I will explain this a lot. We have one photomultiplier, which amplifies the signal coming from the scattered light, and we can increase or decrease the attenuation of that photomultiplier. And we measure here in this area by focusing the aerosol stream, as you can see here, to the middle, and then the measurement. So the hole, which you can see here, is actually it's as big as you can see. but the measurement area where we measure and the focus of the aerosol is of course much smaller. And with that structure, we have very interesting advantages in comparison to other devices, especially what particle size distribution resolution is concerned, and also what the calibration and adjustment. Let's just go back one step. Okay. So I will show you a section of the light path here and here. So this light path is displayed on the slide here. So here's the focus area again. So the light is coming from that side here into. Here's the T aperture, the first T aperture. The light goes in here. The light beam has already that shape. Here in that area, particles are coming from top, and they fly through the optics or through the sensor area here. And as you can see here on the P1 and P2, particles can be in the inner area, fly in the inner area, or fly in the outer area. And this particle, for example, flies in the outer area, and this particle flies in the inner area. And we have a T-shaped optics, a T-shaped aperture on the backside, where the light is going out to the photomultiplier. And with those T-shaped apertures, we form this specific area, measurement area, which looks finally like a 3D T from both sides, either from that side and also from that side. How does it work? Particles, for example, pass the way through the measurement area, and we measure with a photomultiplier a signal and also a signal length. It takes a while until they pass through, and we can have a clear signal. Okay, it's wiggling here a bit, of course, but it's a clear signal. It is coming from particles also in length, which are passing through here. And then we have two dimensions. If we have a particle passing at the border zone here, and the shape of the signal looks like this. So we see here full particle in shape was seen, and here only a portion of the particle. And with that, we can identify, and this is a particle which flew here in that area. If those particles were out in the outer area, they produce a very small signal in height, still more or less similar to that what we see from those particles passing here, maybe slightly lower, but the signal length from here to here is short. Time of time is short. And if we have a particle which is at the outer zone passing, the signal is even lower, and we only see time of flight from here to here. And with that, you can clearly identify whether a particle passes in the middle by the time of flight. The expected time of flight is according to the measured time of flight, with some tolerances, of course. And those particles which are in time of flight too short, we have to decide what we do with them. Some of them we can still evaluate, others we just discard. At the edge of an optical limited measuring volume are measured too small. This is in the outer area here. Yeah. And the wider the distribution, the greater the error, means if I measure more area if this T aperture gets bigger, of course, I have much more decay at the outer side. And this I can see by the signal height and also by the time of flight, and I can diagnose region of flying here at the end. That's very important for us because we do high resolution particle sizing, and with typically with aerosols like salt or VHS or KCl, whatever. And in order to really be exact and correct, especially for filter measurement, for the efficiencies, we need to know what we measure and what the size of the particles are, and whether this is the correct size of the particle. In addition to that, you can imagine that sometimes in such huge area, there are also more than one particle. This is called coincidence. You know this, yeah? So how do we deal with coincidence? Also here we have two dimensions, the voltage again of the photomultiplier and the time of flight. And here we can also clearly see particles which are entering the optics, whether it be 2 particles or 3 or even more, that they form steps. And we can identify them. So we do not look at the total signal. So we really look at the steps. That's why it's so important to have high time resolution of the signal, so that you can identify the steps. Yeah. And we know the time of flight here in that area. Means for those particles which are here in the inner area, we know the signal height. We know the signal height of the second particle. We know the signal height of the third particle, so we can identify whether they are in the middle or at the border zone here in that area. And we then address every particle in combination with the time of flight, the signal height again. So we discriminate the signal. Yeah? And this helps us to identify coincidence and also correct coincidence. Yeah? So this is the time of flight, the correct time of flight. And there was a second particle adding up on the total signal here. And there was a third particle adding up on the total signal. All have correct time of flights, so all can be used. And discriminated, and each and every signal analyzed, we can give for each and every particle the size of the particle. And we do not make the mistake that the size will be overestimated for such kind of a signal, and the number concentration underestimated, because these were actually 3 particles. But obviously, only if we would not do this, we would see it as 1 particle. This is how it looks if we do not correct coincidence. So we can switch it off. Then it will be not corrected. We can see here under different concentrations, 100 micrograms, 8,000 micrograms per milliliter. The signal is getting, total concentration is going down. Yeah. And also the size of the particles increases because of miscalculation of the particle size. And if we correct one coincidence, then it looks like this. So the height or the concentrations, the standardized concentrations are more or less similar for all particles. Number concentrations also fit in total. Very good. And with this technology, we can measure higher concentrations up to that what I showed before. So the most important, how to say, features which we implement not for every device, but where it's necessary, coincidence correction and border zone. So monochromatic or polychromatic light. So what we do
Excuse
is,
me, I
yeah,
want to
of course.
understand the previous slide.
This one?
So you are using different mass concentrations, right?
These are different mass.
So the number
is maintained constant.
number concentration is maintained constant across that.
The standardized number concentration.
Normalized.
The normalized number concentration.
Okay, normalized the number concentration.
Percentage of particles in that measurement. Otherwise, you would have, of course, smaller.
Not the
This is due to the ISO A2 binders standard.
No, the ISO A2 finders, that's the characteristics. Yeah. And the A2 finders, that's the characteristics. And it's measured in different concentrations. And then the percentages or the factors of what kind of size and concentrations we do have.
that is the percentage. That's why it has to come in.
Yeah, exactly. So as I showed before, we do 90-degree light scattering. So there were lots of tests. What would be the best in terms of light scattering, the best angle in terms of light scattering? So you know forward scattering devices, backward scattering devices, other angles. What we saw finally, and there's also a paper which is pretty old already, in 2008, that 90-degree light scattering is for our system best. But if you would do this with a laser source, which is a laser source based on infrared light source, you will have kind of wiggles. I always say wiggles means interferences in between mean and Rayleigh regime, which do not give you a precise and size of the particles. So if you do high resolution particle size distribution, this would be, of course, fatal. Yeah. As you can see here, we are up to 2 micrometers, but the signal could also show 3 micrometers. So that's far away from the resolution we would like to have. And so we used white light particle and white light, in this case, xenon sources, and the calibration curve of the white light source is very clear, constant, monotonically increasing. And this is our calibration function, which we use for the different devices. And we verify this calibration function also with latex particles. So we can clearly say the different sizes of latex particles, because this is the latex curve, it is the curve, that our devices, if calibrated correctly, fit to that curve experimentally. And if they experimentally fit, then we can use this for measurement. So the base is what we always do at the beginning. All particles which enter the optics are in first instance calculated by the latex curve. And then we convert them to different refractive indexes, later to different aerodynamic diameters by volume and by density, and apply different parameters for scattering in order to fit the best to that what is expected in that situation. Ambient air measurement, multiple particles, different sizes, different substances, so not every particle is the same. So if we measure the salt aerosols, of course, then we know refractive index, and we also know the densities, all that that's given. But if we measure ambient air, we don't have that. We can only estimate on it. And this is then the algorithm behind the system, which converts measurement based on the latex curve finally to the PM values. So the capability of such kind of a system, we are not at 0 here. And so the calibration curve always ends at 0. Means if there is no pulse height, then there's no signal. if there's no signal and there's no particle. So that's the point 0. So it is there. And for calibration, you typically need 2 points. But the first point an optical measurement is 0, no particles. So you test the system. The HEPA filter, no particles, okay, 0. And then you can take one of the points of that calibration curve, one size, and test with one size. And that's all what you do. So you adjust the photomultiplier voltage so that the signal which is coming from photomultiplier fits to the calibration curve and the respective size of the particles you suspended. This is the normalized, and we know the optical size of those particles which we have tested them before. How is it going? So we have here different calibration curves or different photomultiplier voltages. For example, the correct setting would be 1050 millivolts for the photomultiplier voltage in order to size particles correctly. So if the signal is too low, if, for example, for a 2 micrometer particle, you would have expected a signal that would be 2, 3, but it's only next to 1. Then we increase the photomultiplier voltage so that we finally get this particle on a level that we signal height for that particle according to the lattice curve. So this is what we do. So we move this calibration curve up and down or in this direction in order to get it fit to one single known size of particles, optical diameter. And then the complete system is calibrated. So we don't need to calibrate each and every size. So it's one size which we can use for the calibration. Then the complete calibration curve moves due to the amplification of the photomultiplier. So it's only the signal from the photomultiplier finally. Of course, if the light sources are too weak, then we get problems here in the lower area because the light source is too weak, so we have no resolution. But the light sources which we use are made for these specific ranges, and we can tune our systems also to other ranges by more or less amplification. Okay, there are some points where I say we can amplify even higher to see maybe more smaller particles, but then we have already interference with the gas molecules. So you see light scattering, which is actually not existing, and this is next to 117 nanometers in that area. So that's 175, that's the lowest. And for these light sources which we use, we have other light sources, stronger light sources, then we go down to 120, but not for emitter measurement, also not necessary. So PM voltage, too low, should be 1050. This is the situation. Full side is too low. We increase the photomultiplier voltage and finally end up at a size which is correct to that what we expected to have. And this over the whole range. That's our calibration feature. And you can do this easily in the experienced on the device. You will see it later. You can test it by yourself. That means that's done. And it's exact. What do we do this? We do this with our so-called monograph. This is a dust, which is silica oxide of a certain size, approximately 1.5 micrometers in size, but optical diameter is 1.287 micrometers. And the optical diameter will be determined of that dust by our reference spectrometer. So the reference spectrometer is calibrated with latex particles. And as we always use the latex curve for calibration, we can check then this dust, what optical size it most likely is. And it's typically in that area, 1.287 or channel number 140.3, sometimes it's 139.9, but it's in that area. And for all devices, all optical devices in a certain range, from 180 to 18 micrometers, the channel will be, if you apply that dust, the signal should appear in that area 142. So we find this on the bottom, and then we just look whether it fits or not, and if not, then we. So if we calibrate it, if we know the size of the monodust and determine the channel, then we can go to the candidates and apply the dust, and then you will see a clear signal. This is the background signal, and it's so dominant, and that signal will be analyzed, and the mean diameter will be given. And based on that, we adjust. You can do this. We do this in our. Actually, we have two calibration methods. Of course, factory calibration. We do monodust calibration in front of factory calibration, and factory calibration is then done against any aerosol because we are just checking on the correctness of the system against the reference system. So we can take any aerosol in this case. We take an ACL as an aerosol. We dispense it, dry it, and then we have a convolution of candidates in a room, additional references in the room, and against those we compare. And the PM values and also concentrations should be next to plus minus 2% in comparison to the reference instrument. And this is then fine in the certificate. And if you then do ambient air measurement, the reference instrument is the instrument which we used at the TÜV for the certification. So it's still existing. And out of that, we breed different other devices which we then use for the calibration. And then these devices measure inlet tolerance to either with high uncertainty or with low uncertainty or high R square more than 0.95 against each other in linearity outside, if you remember, in the air. So very precise to each other, and all then have their own algorithm. Algorithm, and that's why they measure in linearity against each other and also in linearity. We don't need to do that ambient air test later, so it's just enough to do calibration with monodust first, then candidate against reference, and then no ambient air measurement for tracking or something like this is necessary. But you can do this, of course, and we sometimes also do this, also against other devices, but to do this is not necessary. This is how it looks like on one of our devices. So here's as you can see here, it's the particle size distribution of the ambient aerosol, or indoor aerosol in this case. At the moment, here in that picture, the deviation is 140 plus 2 because there was no monodust applied. Then we apply monodust, and we see a deviation of minus 1.2 channels. Means the particles are undersized. And then we click calibrate, and then the system automatically tunes the photomultiplier voltage to value, and the deviation is minimized. It will be sometimes it will be 0, as long as it plus minus 2.3 on good. At 3%, for example, or 1%, one channel deviation, then we had around 3% deviation of the PM values. And total uncertainty is 25% plus minus. So one channel is unproblematic, and 3 channels or 4 channels, yeah, then I would suggest to recalibrate the system, which you can do then again with monodust on site, or we have also possibilities to see the drift of the system, especially with the bluish light of our system, of our feeders regulatory monitoring system, but all the others which are working with the bluish LED have the same appearance. So here you can see an anomaly in the spectrum. That's due to the Rayleigh-Mean transition area. And this is always, because it's dependent on the light source, always at the same point. And if the system, this is the raw signal, if the system drifts, means optics is spoiled or the LED source is decayed, then it breaks from this direction. And we monitor that point, and our system is channel deviation. Means it shows what the drift actually over a longer time is. Yeah. This, of course, always depends on the aerosol. If there are, if you have very clean area, clean air, and not lots of particles here in that area, it's 0.6 micrometers, then you will most likely not see this, and then also the system will not see it. Yeah. But if you do have clean area, clean air, the M values are mostly very low and also not critical. So, but if there are also significant number of particles here in that area, then we can see it, then we can track it, then we can alarm. Yeah. So if you install a system somewhere, and you get this also reported, the channel deviation, and you can see if there is a drift or not. And if there's no drift, then you don't have to go there. If there's a drift, then you observe first the data. And if you see yes, it looks as if there is, due to high pollution, whatever, then you go, and the first thing what you do is recalibrate with monodust. And if you did this, after a while, if you reach a certain amplification voltage next to a certain value, then you decide, okay, let's clean the optics. And cleaning of the optics, we can also show this, is easy. Yeah. And calibrate the system with monodust again, because then you size particles too big, because then when the optic is cleaned again, then sizing is too big, and you have to bring 40 multiplier voltage back to normal. And typically is the 40 multiplier voltage, then the 40 multiplier voltage which we had at the calibration. So that's a very interesting and very important point if you do unattended measurement in which are not good reachable. We do have devices which are more compact. So this is also a device FAM certified EN16450 for enhancement of existing measurement networks. It's called FeederSmart 100. It's a compact device, and you can install it directly outside. It's very convenient. Here. And I will show you some data which we gathered in Finland recently at a campaign with the Finnish Meteorological Institute. Here you can see this is against reference, against barometric samples from metal, and the expected uncertainty for that device under these conditions, humidity conditions and temperature conditions over half a year, more than half a year, at 30 micrograms per cubic meter was 8.43%. And R square 0.967 against barometric. So that's really enormous. I did not expect it to come out in that way, because there are lots of different aerosols in Finland, especially at the end of the season, salt, you have other aerosols which you do not typically expect. So proofs, and also with small devices, you can get good measurements, and you also easily meet the criteria of 25%, and this with low correction factors after the correction of the data. So we see to a slope of 0.972. And if now that point of this limit here where the uncertainty is calculated, in Germany in Europe for PM 2.5, it's still 30 micrograms because uncertainty is always against a certain point. If this will be reduced, you can imagine that the uncertainties here in that area are higher than the uncertainties here in the upper area. If there are no particles or less concentrations, less particles, higher uncertainties, we need to survey with that data from Finland, and we can see that if Europe reduces to 20 micrograms, means minus 10, that we are still in uncertainty better than 25%. So we slip, of course, yes, we do. That's normal, but we are still at 25%, plus minus. Other systems, and this we also know, if you do have initial higher uncertainties, especially for regulatory elements, then it can happen that you are out of that area plus minus 25%, and then you're not compliant anymore. So for us, also, we see that it's perfect. Those systems can be used also for regulatory measurement and also fit to the new standards, which will come in the future. Good. Those systems are used. Let's just jump back. Also, for example, for fog measurement, this device, we measure a fog at different locations at higher altitude in observatories, and also cloud droplets in these devices, with particles up to 40 micrometers, with a separate duct where we draw the particles from. And so they are very flexible. You can use them, optical particle size spectrometry, you can use them in lots of areas. We can meet the compliance. We have features which give you deviations. We have easy calibration and adjustment, which is good for networks which have lots of devices, and we still comply, although if the uncertainty budget which will be reduced in the future in Europe. And that's for aerosol spectrometry. What I want to show is that we have also indicative systems called AQGuard Smart. And here is displayed what we do with those, besides particulate matter measurement of those, which are also pretty good in uncertainty, minus 12%. We can attach gases, we can attach, for example, audio, we can attach a meteor station, we can also attach black carbon and other sensors, additional sensors, no low-cost sensors, high-end sensors, typically to that device. And then this device completely reports, for example, to our cloud. We have our own cloud called Microsphere, which everybody can use with our devices for free, or also to other clouds via MQTT protocol. And from there, you can pick the data if you like. If you have your own cloud, then the device can report directly to the cloud, to your own cloud. This is for flexible measurements, hotspot measurements, easy to deploy, easy to gather the data, and the system itself, the cloud system, which we have, has various possibilities of displaying the data and also analysis of the data. So somebody would like to try it. You can also integrate other devices as long as they are capable to be integrated. And yeah, just feel free to ask. Nano, let's just give some impressions on Nano. Nanotechnology, I mean, I don't have to tell you something about nano and CPC measurement and SMPS measurements. Of course, we also measure nano with our systems. We have dedicated systems for the measurement of ultrafine particles in ambient air, which are very compact and flexible. Typically, also the operating system is always integrated, so you don't need separate laptops. That's for all of our devices. And of course, also neutralizers. Out of that, we form SMPS systems of different, for different applications, not only for ambient air measurement, but also for our test rigs or any other laboratory measurements. And we also have a arm, which is pretty good, which can be attached also for comparison against CPCs, for example, or recalibration of CPCs. So this is the portfolio. Different DNC systems, different columns of certain sizes, very huge columns, from 14 to 1,400 nanometers, smaller ones, and this is the standard column, 4 to 1,200 nanometers. That's the medium column. That's typically used for ambient air measurement. And we do have different condensation particle counters for different concentrations. We don't like to dilute, so we dilute by our optics. It means we measure only a small portion, but statistically with low uncertainty. So we decrease the area where we measure, and with that we can measure up to 2 million particles per cubic centimeter with our piece. And in nephelometric mode, because every CSPC has also got a nephelometric mode that's calibrated nephelometric mode, 10 power 7 particles per cubic centimeter. They are used for laboratory measurement, but also for environmental measurement and predominantly for environmental measurement. So just to give you an impression, France, for example, I would say 95% of all systems, which are approximately 70, are from PAS. They have a regulation behind since 2018. UFP needs to be measured because it's hazardous. And we managed with our distributor to bring those systems in, and they're very convenient systems. We measure in the AIDA cloud chamber with our SMPS systems and also CPCs, brake emissions, environmental monitoring, of course, and also in our filter test systems for HEPA filters. So there are various applications where you can use such kind of systems. For example, also at the airport in Zurich, with our system, with a specific feature, we had a valve where we can switch in between directly air coming through the inlet directly to the SMPS or through a catalytic stripper. Yeah. And with that, you can determine what is volatile, what is not non-volatile. And this is what Zurich is doing since years. They try to find out, okay, what's the volatile component, what's the non-volatile component, and the volatiles typically come from the airport, and the non-volatiles typically come from somewhere else. With that, they determine, or they can see then what emissions are coming really from the airport. We set all items unattended measurement. This one huge topic. Environmental measurement according to European standards, of course, HEPA ultrafilter testing, and they can also be combined with our aerosol spectrometers. Means we can form complete particle size distribution from, for example, 10 nanometers up to 40 micrometers in combination. Specifically, what do we do different to that what others typically do? We have a maintenance-free saturator design. So this is the saturator. So this is a helical shape, inside helical shaped area The butanol flows through and will be evaporated by heat. And we have an active fluid management. Means we pump butanol into the saturator, but we also pump it back to the reservoir. With that, we can place that bottle, for example, a bit more far away, not directly on the superseat, but a bit more far away, maybe also in a safety cabinet. If you see that this as a requirement, especially if you use reservoirs here which are more than 1 liter. So you can use reservoirs 2.5 liters, 5 liters, for example. Yeah, and place it in a separate cabinet, and then hoses are going to the CPC and then manage the fleet. Obviously, the kind of how optical particle of nanoparticle counters work. Condensation process, droplets will be formed, and we analyze the droplets in terms of signal height.
The Q&A, so you can.
Yeah, okay, good. So what you see afterwards is a particle size distribution. And the particle size distribution gives you an indication of the quality of the condensation process. So it's not only the signal height, it's a particle size distribution. And you can always compare it against our standard values. And the second is we do have a very comfortable device status reporting. So all parameters which are critical for the condensation or even for the sizing will be given by the system and also reported. Yeah. By the respective protocols which you can use. And we do have here underneath a liquid level sensor control. And the liquid level sensor, that's something which we implemented recently, shows you whether the bottle is nearly empty and then gives you for 2-3 days to refill. Yeah. Other devices say, okay, particle size too low, signal too low, please refill butanol, and it's already too late. We want to have it different, and that's our solution. This is a complete system, compact system. So there's the feeders system for optical particle measurement of PM, and a complete SMPS in one cabinet. Size, I think it's less than a meter in height and 60 by 60. It's climatized and mobile. You can place it where you like and measure both particles and also PM in most devices. Yeah, and this is particle size, full particle size distribution. Here in number concentration, as you can see here, ultrafine particles dominant, and the optical particles, they are mostly less. Similar to the weight, ultrafine particles contribute only 8% here in this case, and the dominant mass is coming from the feeders system for the optical particles, of course, because those particles which are huge in size contribute, of course, quite a lot of mass to the system. Yes, you can always see what you are scanning. You can set these values directly on the system, and you always see whether you are in a range, in a scannable range. And based on the scan time, you also see whether the resolution you are scanning over the range which you set here is comfortable, or is low, or is high. Also gives you instantly the idea of, is it a good scan, or will it be a good scan, will it be not so good? And what we also do is residence time is often a very important topic. You need to know from the column to the patient particle counter how long it takes until the signal appears. And this we can determine by function which we integrated. So we do both down scan and up scan and average scan, and then the measurement, the residence time will be then determined by the system, and this you then set after validation into your system. It will be not automatically set because sometimes scans are not so good, and you use a scan maybe you set it finally. And we do counter comparison. For example, you can attach 2 counters to our systems and then directly compare for quality control, for example, on site, and you get a factor counter 1 to counter 2, and this will show you whether you're still in range or not. So these features, all these features, also the attachment, for example, of CDCs, which are from third-party manufacturers, yeah, to our emission control unit. These are all features which help to enhance and also to control the system as convenient as possible. It's always our aim to make it not too complicated. Everything on the device, everything can be managed directly on the device. You don't need to have laptops or whatever. You can directly manage every function on the device itself. Then, of course, those kind of functions are also implemented. Yeah, this here you see, for example, combination our DNA or DNC control unit. Plus or CPC, which is high against combined with our DNC control. And it's a system which you can enhance by certain functions, specific functions easily. We help you if there are functions necessary which you would like to have, let it be transporting data to a certain server or logging every 5 minutes data in a special file which is then uploaded via FTP, whatever. This is all possible and directly on the system, you don't need data. Here you can see the French network. This is some years ago, but finally or recently we covered from the it's a big success also for us and also for our discipline and very good performance. Yeah, diffuse charging, just a short glimpse into it. APGAR Smart 2000, diffuse charging principle. Diffuse charging means you charge particles unipolar, and then you analyze the charges, and out of that you calculate concentrations. And we do have one diffuse charger as well for hotspot measurement in the area of 10 nanometers up to approximately 1 micrometer. It will give mean diameter and concentrations, which are totally okay, in my opinion. We use these devices for hotspot measurements, for example, also in Italy. This was in Italy. And or in airports. And here, for example, the results, you see here increases of ultrafine particles measured, depending on the wind direction, of course, always. And in addition to that, also NO2 increases, and they point clearly on departure and arrival of the ferries in the area. So this was actually a study, and concentrations are pretty high. 7,000 particles can be even higher because we never measure directly in the plume. We measure it on sea level, and the ships are, of course, pretty big. So that's from my side. Thank you for listening. Yeah, I would like to give you the time to play with our instruments, if you like. And with that, I would like to close my presentation for a moment. And if there are questions, just let me know.
Diffusion charging is a charged aerosols you are measuring. You're measuring the charged aerosols.
Diffuse charge.
First slide you are shown diffusion charging.
This one?
Last slide.
Next one?
Our graphs you are showing.
The airport.
The airport.
What is this?
Okay. Okay. This is ultrafine particles concentrations. Here. Ultrafine particles.
What do you mean by diffusion charge principle?
The diffusion charge principle. This principle. Yeah. Diffusion charge principle means that you take clean air with a corona, you use ions, unipolar, and the particles, these ions will attach at the particles. And then you can, depending on here in this kind, the clamp electrode, check how many electrons are at particles, and with that you can deduct on size. Yeah. Of course, there are some assumptions made always, because it's not the real size. So you should have an idea of what is typically going on in the ambient air, so that you have a correct number concentration finally calculated. That's how it's going. And it's a principle which is quite old. But for ambient air measurement for ultrafine particles up to 600 nanometers approximately in the area, it's strongly coming up in Europe because it's cheaper than SMPS systems. You get mean diameters. Sometimes for some devices you also get size distributions to a certain extent, depending on the environmental conditions, which are quite good. But mean diameter is most of the time probably enough. So if you have low mean diameters, small particles, then they are coming from combustion. If you do have particles in size, mean diameter next to 100, up to 150, 200, then this is typically old aerosol, ambient aerosol, background aerosol. With that, you can identify sources to sample.
You were telling about you are not diluting the samples. Instead, you are sampling only a portion of aerosols.
Yeah.
So can you explain that? How?
Yes, I can explain. So, just jump back. Sure. Yeah. Okay. So, we have this focus area here in the middle where we measure the aerosol. So we focus the aerosol into the measurement volume, as you can see here. And of course, this is only how to say it, simplified. Yeah. The area here is of course much smaller than the orifice here. Yeah, the dimension is not correct, but otherwise it would be too huge. So what we can do with this T-shape culture in front, we can even make it more narrow. And then we only analyze a small portion, even a smaller portion in light scattering as for those where the T is wider. Yeah? Light scattering takes only place then in a smaller area. So if you do have high concentration, typically you do not need to analyze everything. Statistically, it must be representative. Yeah? And by narrowing this area here, is we have that T-shape, or by completely open it, yeah, we can tune the systems more light scattering, more particles measured, or less light scattering, less particles measured. But for high concentrations, we need a certain statistics. Means if we have low concentration, and for example, and then a sensor which is used for very high concentrations, more than 1 million, then we have bad statistics in the lower area. Yeah. So if you want to measure then 100 or 10 particles per cubic centimeter, then this is not possible because there are not enough signals really to determine particle size distribution. This is how we do this. Yeah, we enhance or we decrease, and of course also the optics will be modified to the sensor in the way that it fits. The analysis area of the light scattering.
Basically, the beam itself is very small.
Yeah, the beam is very small.
It is very small.
Yeah, the beam is small. The beam is very small. I can show you at the devices here. And then we analyze that area in concentration and particle size distribution. And for ambient air measurement, we have a specific sensor which goes up to 20,000 particles per cubic centimeter. For SMPS systems, we typically use full flow sensors which go up to 10 or 100,000 particles per cubic centimeter, which are also good in low concentrations, especially for SMPS. Also very low concentrations.
The saturator also, you are telling there is no wick. There is no wick, how
Yeah.
it will create the
Yeah, that's it. Have wick. So it's also nothing which you need to exchange regularly. It cannot harden. It will not get dirty. We have a continuous flow of ethanol, or intermediate flow of ethanol, always enough, and in a way that we do not produce particles when we pump it in, because if we would produce particles by the pumping, then we see them, and if we see them, then we do force measurement, especially at the assembly system. It's really from the structure in our structure to it in a way that we have a continuous flow of ethanol, which is then evaporated, and the residual ethanol will be then pumped back to the reservoir.
Hello. Just wondering, because your this probe has very wide particle size range, like up to 100 micrometer that you shown.
Yeah.
Just wondering, because you on the scattering principle, mis-scattering actually to work really maybe less than 10 micron, because your large angle scattering is more in that range.
Yeah.
So for larger particle, it is forward scattering will be more. So how that things are behaving in this case?
You're correct. Typically for bigger particles, forward scattering is the solution, but we don't have forward scattering. We have 90 degrees light scattering. But what we do, the signal is very, very small. So we have to amplify it anyway. Yeah. With a photomultiplier. A sensitive photomultiplier, so every signal coming from here will be amplified. So if the signal is higher because particles are bigger, then we reduce the amplification. Of course, we always also then reduce the lower point of recognition of particles because we cannot amplify them anymore. The signal is too small, then we cannot amplify. But what we can do with a photomultiplier, we can have, for example, for our systems, different size ranges measured. Means, for example, from 0.3 to 17 micrometers, or 1 micrometer to 100 micrometer. And that's due to the fact that we amplify the signal. And if we would have, for example, a 100 micrometer particle in a range where the system is set for 170 nanometers up to 30 micrometers, then the signal would be much too high. Yeah, so we cannot identify that particle anymore. Yeah, and so that's why we have to reduce the photomultiplier voltage, and then we can also clearly identify those particles and differentiate those particles in size again. So that's the background. So we tune the system with the photomultiplier to the different ranges. And then, of course, you also need to use different dust for the calibration. Yeah. So if you measure in the size range from 1 micrometer to 100 micrometer, you cannot use our monodust anymore because it's at the lower edge. The signal is already quite problematic, and then it will give you not good results. So then you use a dust which is bigger in size, or you use your latex particles. That's then the easiest way. Because for that, you know,
select a particular size range for particular operations.
Yeah.
Yeah, we have to select a particular size range for this.
Yeah, we can change the size ranges. We have typically 3 to 4 dedicated size ranges for instruments. For the ambient air measurement, for the ambient air measurement of particulate matter for the regulatory module, it's typically up to maximum 20 micrometers. And starting from 175. Most of the particles are next to 200, 300 in number concentrations, but the big particles are also very important because they dominate them.
having stand our speaker. Everyone is encouraged to come look at their system. We have tea also arranged in the legs. So thank you thank you everyone. So everybody, we are here the entire day. So there are, if you want individual presentations or individual discussions, you can let us know and we'll be at your, you can come here and see.
The size range here for the system is too high. It's better to start at least 0.2.
This is the one for air.
So these are two different sensors. One for medium concentrations. Yeah.
It's range of
Have different different options. One is the wide area number concentrations, and these are high concentrations or higher concentration sensors up to 200,000 particles sensors, which maybe up to 2 million. And we need them for this because we have very high concentrations coming from the aerogeneration, dilute. And for HEPA filters, you need to have really high concentrations, but we don't want to dilute in front of measurement. The dilution is always an uncertainty. Yeah, you never know. Okay, what's the dilution? That we measure with the high concentration sensor on the upstream side, and we can low concentration sensor on the downstream side, and then we can, for each particular size, determine the particle size fraction efficiency.
What's the inlet difference?
This is here.
It's going just down.
Yeah, there's a tube which leads to the device. Here are the pumps. Here. And this is the light source is in the device itself. Yeah, this is the light source. That's the white light source. Yeah.
But this beam is so big. You are doing very small.
Yeah, but this is not the beam.
You said there is an eye base.
Yeah. There's a T-shape such as and then we have lenses who guide this to the area which is in size less than a micron. And less than a millimeter.
Like laser light, we have alignment. For me, there is no concern.
No, because we align not the laser, we align the amplification. Yeah? And it's this is not necessary. We first go by the photomultiplier increase of the amplification voltage and nothing else.
It is more lifetime than laser. So this LED.
The added power is more or less similar. But they are easier to handle.